Steel Research A Global Journey. So my name is Jiyoung Gang, and it is my pleasure to be your chairperson today. So Harry has been my supervisor since 2008, when I have joined GIFT postdoc in South Korea. And he has been also my advisor when I went to Cambridge for my PhD. And I think I can still call him as my advisor, because whenever I come upon difficult issues, I imagine his response to overcome them. So let's welcome our first speaker, Professor Colin Humphreys, whose talk will be on semi-metal graphene to challenge steels. So Professor Humphreys, please.
Hi, well, thank you very much for that kind introduction. And it's a huge pleasure and a privilege for me to speak in this webinar series, because I've known Harry Bhadeshia for many years. And it's just a huge pleasure to give this talk. And he's been my friend. And, you know, I look up to him as a fantastic scientist who knows so much more about materials than I know about materials. So it's a great pleasure to do this. So thank you for inviting me to do this. I should say I have 3 addresses up here because I was at the University of Cambridge and I still have a desk there, which is very good. But I had to retire because of my age, as Harry is having to do. And I was then given a job at Queen Mary, a professorship at Queen Mary in London. And so I worked there. And I also set up a spin-off company called Paragraf. So I worked there as well. So I got 2 jobs. So I'm actually working very busy, as I've always done, and as Harry always does. So graphene, let's start with graphene. It's said to be 200 times stronger than steel. So this I looked up on the University of Manchester website. I looked at this today, and it says on their website today, the revolutionary properties of graphene, 1 atom thick and 200 times stronger than steel. So of course, Manchester University is where Guyam and Novoselov got their Nobel Prize for discovering graphene. So graphene's on the front page of their website, and it says 200 times stronger than steel. And this is another quotation, and it's a quotation from Professor Hone, and it's something he said at a press release based on a paper he published in Science in 2008, when in that paper, his group measured the strength of exfoliated pristine graphene. But then in the press release, he apparently sort of extrapolates their measurement, because he says, our research establishes graphene as the strongest material ever measured, some 200 times stronger than structural steel. It would take an elephant balanced on a pencil to break through a sheet of graphene. So, you know, it gives the impression that large area graphene is still 200 times stronger than structural steel. So who's the very best person in the world to question this statement? That person, of course, is Harry Bhadeshia, the king of steel. And so he's got a very nice 219 video on YouTube. I'm just going to quote from that. So his video is called Introduction to the Strength of Graphene. And he says, the tensile strength of perfect graphene, a small piece, 2 microns by 2 microns, is 125 gigapascals. But the strength of small crystals, he points out, is size sensitive. And so he says, quite rightly, of course, there's no, you shouldn't talk about strength without specifying the size of these small crystals. And as we know, configurational entropy favors the formation of defects. So all macroscopic materials contain many defects, and large objects contain more defects than small defects, of course. So Harry says a 2 micron single crystal of iron along its weakest direction has a tensile strength of 14.5 gigapascals. So a 2 micron size, if you compare a 2 micron size piece of graphene with iron, then the graphene is only 8.6 times stronger than iron and not 200 times. So this statement is just incorrect. And also the generalization to larger sizes is very incorrect, because as Harry points out, at larger sizes, iron and steel are stronger than long carbon nanotubes and stronger than a large sheet of graphene. So we can conclude graphene is most unlikely to replace steel. And Harry's video is just a beautiful example, giving these simple arguments, showing that this statement which is still on websites around the world, and I still hear it in talks, this statement is just wrong. So I'm going to ask in this talk a related question. Could graphene replace silicon? So silicon is the beating heart of functional materials. Silicon is to functional materials what steel is to structural materials. And laptop computers have over 200 billion silicon transistors in them. So, you know, each of us owns, as it were, billions and billions of silicon transistors in our houses, in our cars, in our workplace. So silicon is just a really important material. And arguably, we're living in the silicon age because it's in just so many things which we have. It's in washing machines, it's in dishwashers, it's in computers, mobile phones, televisions, cars, and so on. So silicon, tremendously widely used, as steel is in structural buildings and so on. So what I want to ask in this question is, in this talk is, could graphene replace silicon? Could it be that we have transistors which are 100 times faster if they're graphene transistors? Could it be that graphene transistors will consume 100 times less energy than silicon transistors? And that's a really important question at the moment because, you know, data centers, which have huge numbers of silicon transistors in, the International Energy Agency said that by 2025, data centers would consume 20% of all electricity in the world. And by 2030, they probably consume 30%. And so if we can reduce this consumption, and I should say it's very hard to stop this. You know, you may try and stop people flying in planes, you may try and stop people eating meat and so on. But, you know, to stop people using their computers and mobile phones, that's going to be extremely, extremely difficult. So there's a real need to decrease the energy consumed by silicon transistors in things like data centers. And the basic scientific reason why silicon devices consume quite a lot of energy is because they have quite a high resistivity. And so that means that the energy, that the power they consume is large. And so if we could replace them by graphene transistors, this will be really important for the future. So it would be revolutionary and transformational. So that's the question I'm going to ask. I'm not actually going to answer it at the end of this talk, but I'm going to give pointers to an answer. So this is now what I'm going to talk about. I'm going to go a quick introduction to graphene, and then the high expectations everyone had of graphene. And this was really because they were using small flakes of graphene, as we'll see, which have remarkable properties. And the hurdles to industrial application are because of the problems of scaling up. And then my own involvement in graphene, which I put down to serendipity. Serendipity is a strange English word, which means good fortune and good luck. And then the new graphene solution we came up with, a new method of growing graphene by a technique called metal organic chemical vapor deposition, MOCVD. Then our first product, which is a graphene magnetic Hall sensor. I'll talk about future potential graphene products. And then I'll ask the question, just pose it at the end. Is it a possibility that graphene could replace silicon in transistors? So let me move over these items quite quickly because many of you will know this. So in 2010, two Russian scientists working at the University of Manchester, Adreil Wong and Kostya Novoselov, they got the Nobel Prize. And this was a citation for groundbreaking experiments regarding a two-dimensional material, graphene. And as Harry has pointed out, graphene is actually a three-dimensional material because it's not just carbon atoms in a two-dimensional plane. These carbon atoms have pi electrons above the plane and below the plane, which give graphene a thickness. So it's actually a three-dimensional material. Physicists tend to think of it as two-dimensional, but you know, material scientists think of it as three-dimensional. And it's also unusual for a material to win a Nobel Prize, right? Steel has never won a Nobel Prize. It's very unusual. They got the Nobel Prize for this isolating and doing experiments on this new material. So graphene, a two-dimensional network of carbon atoms. In England anyway, we sometimes call it carbon chicken wire because chicken wire has a graphene structure. And I'll show you this in the next slide. And graphene is remarkable because it is the first material in which all the atoms are in a single plane. And that's why it's called a two-dimensional material by the physicists. And it is, I believe, the thinnest material in the world, because when you take into account its thickness, because carbon is such a small atom, I think it's the thinnest material in the world so far anyway. And so on the left-hand side, if you keep chickens and you go out and buy some chicken wire to keep them in a cage or in a pen, then that's what chicken wire looks like. And it's the same sort of hexagonal arrangement that graphene has. And then if you stack graphene layers one upon another, you get graphite. If you peel off a layer of graphite, you get graphene. And this was done in 2004 by Gaiman and Vosilov. They isolated graphene from graphite by using sticky tape on both sides of a lump of graphite, and then they pulled the sticky tape apart and got two blocks of graphene from the original first block, put some more sticky tape on, and kept pulling it apart until they got down to a single layer of graphene. And then they performed really difficult experiments on graphene. They were difficult experiments because a single layer of graphene is transparent. And so to do experiments of something you can't see is really very difficult. So that's a key reason they got the Nobel Prize. It wasn't just for sticky tape. And I should say also, the graphene flakes and powders, which do have, reasonable mechanical strength, they have been used to add to car tires and concrete and tennis rackets and so on, and running shoes, and it is said to improve their performance. And I think in some cases it does. For car tires, it may improve the thermal conductivity of the car tire, and so the car tire remains cooler, and so that extends its lifetime. And for concrete, it may improve the resilience of concrete. So graphene flakes and powders are increasingly added to these products, and then they can sell products for a higher price. They put on the front of the box contains graphene, like your computer contains Intel. But if we want to make electronic devices from the graphene, then we need to have larger area graphene. For example, silicon devices are made from silicon balls, which are 12 inches or 300 centimeters in diameter. So 300 millimeters in diameter. So we need larger area graphene. You can't manufacture devices using sticky tape on blocks of graphite. So exfoliated graphene flakes, the Nobel Prize winners found graphene has extremely high electrical conductivity. They said 1,000 times better than copper. Because of this, very low resistivity, and therefore that's the reason graphene promises very low power consumption, lower than silicon. Graphene is also very flexible. It's very high thermal conductivity, so it promises increased device performance because a lot of devices, their performance is limited by the temperature at which they run. And I used to work in gallium nitride, and gallium nitride power devices can only operate at about a third of their theoretical limit, and indeed experimental limit, because of the heat that they generate. And so they just get too hot and it can't be conducted away quickly enough. So increased thermal conductivity enables you to have power devices which you can get the heat away from. And graphene also has high optical transparency, and that promises to have transparent conductors replacing something called ITO, which is indium tin oxide. And indium is on the world's list of critical materials. So because it's very scarce. And so in the future, to prevent us running out of indium, then having a material to replace it is very important. So flakes of graphene had promised all these desirable things. And what's remarkable is all these world-leading properties are in a single material. And so it is a material which is unique in the world, and it's sometimes called the wonder material. And so it's called the wonder material, more conductive than copper, more transparent than indium tin oxide, and people often say stronger than steel, which we now know is misleading. And there's been huge attempts around the world to scale up. So the problem is, if you want to, it's like structural materials. If you want to use them, you've got to scale them up from the laboratory. And so we need to scale up from these tiny flakes you get when you exfoliate graphene from graphite using sticky tape. And people believe this would be easy to start with. And IBM invested over $3 billion in trying to scale up and get graphene you can make devices from. Intel invested over $750 million and Samsung over $2 billion. And these companies have largely stopped this intensive research on graphene because they failed to scale up to have a graphene that they can use in electronic devices. So the problem has been in scaling up. So you can say, where are these predicted wonder products? And so IBM, for example, this is the left-hand picture, they assembled a graphene transistor by hand. So they had tiny flakes of graphene, transparent, and they made this transistor by hand, and it was 10 times faster than a silicon transistor, but they couldn't make it, couldn't manufacture like this. Samsung made transparent graphene contacts, but again, very hard to manufacture like this. And Bosch, on the right-hand side, they made a graphene Hall effect sensor and said it was more sensitive, 100 times more sensitive than a silicon Hall effect sensor, but again, it was assembled by hand, and you couldn't manufacture like this. And this just gives some of the newspaper headlines which have been around about graphene. So on the left-hand side, this is a headline from the World Economic Forum newspaper, and they say graphene could soon make your computer 1,000 times faster. And I think that this headline was put out over 5 years ago. And of course, we don't have graphene computers 1,000 times faster. It hasn't happened. And then on the right-hand side, it says graphene filters change the economics of water. And as far as I'm aware, there are not commercial graphene filters that have changed in the economics of getting desalinated water. And then in the middle, Bosch finds graphene magnetic sensor 100 times more sensitive than silicon. So the whole problem is these results you can show in the laboratory by assembling things by hand using graphene flakes, but the challenge is to scale up to have larger area graphene. And when Bosch made their graphene Hall effect sensor 100 times as sensitive as silicon, they issued this press release, which they said they created this sensor, but then they added these words in their press release. This is unlikely to compete for 5 to 10 years. Let's compete with existing sensors due to the current lack of large-scale, wafer-based and transfer-free synthesis techniques. So what existed in 2015 and what exists now is large area graphene, typically 4-inch, which is made using a technique called chemical vapor deposition, CVD. And in this technique, gases like methane are deposited on a heated copper substrate, and the copper's there because it acts as a catalyst to decompose the gases like methane. So you then get graphene on copper, and the copper substrate, some of those atoms get into the graphene, so it's contaminated graphene. And then when you want to put the graphene onto a more useful substrate, you have to transfer it, and that puts more impurities in as well. So it's very difficult to use this method for making electronic devices because of contamination and the problem of transfer. And the graphene you can go out and buy is on the left-hand side, exfoliated graphene. In the center shows a layer of this CVD graphene. And on the right-hand side, you can get graphene powders and graphene oxide powders dispersed in water. And those are the things that you can go out and buy. Now, let me tell you about my involvement with graphene. So this is a sort of a diversion, but an interesting diversion, I think. So graphene was isolated in 2004, huge publicity, we all know that. And many scientists moved in to work on graphene at that time. And I and some other people, many other people avoided this because there was so much hype. And I was very busy working on gallium nitride then. And so I deliberately avoided graphene and decided not to work then. And in 2014, I was invited to talk at a conference in India about my gallium nitride research. And after the talk, this happens in many countries. You go and talk and students will follow you around and say, we want to come and work with you, want to be a research student, want to be a postdoc. And so I had people following me around. There was a particular Indian student who was very persistent. She was called Priti Gupta. And she said, let me tell you about my research. So we sat down, had a cup of coffee outside the conference hall, and she showed me what she'd done on graphene. And she got a home-built CVD system, and she'd and she looked with the electron microscope at the structure of graphene, and it was really poor quality graphene. But you know, she was very bright, and she struggled, and she got these electron microscope results on really quite poor quality graphene. So I was really quite impressed with her, and I said, "Look, I think you're really good, but I've taken a decision not to work on graphene." And she looked at me and said, "Professor Humphreys, you're absolutely right." She said, "You continue working on gallium nitride, but I'll come and join you and I'll work on graphene and we'll collaborate and together we'll make a graphene gallium nitride device." And I thought that was such a good answer that I said, "Okay, I've got something called an EPSRC platform grant, and this provides flexible funding, and I've got money on this, but I can employ you for a year. So if you're prepared to come over to England, I can employ you for a year, and we'll try and do what you just said." So that's what we agreed. And I then was working on gallium nitride with a person from Manchester called Phil Dawson. And I said to Phil, "Can you arrange for me to meet one of these Nobel Prize winners called Kostya Novoselov? And can I have a discussion with him about making a graphene gallium nitride device?" So in 2014, I met Kostya in his office in Manchester, and we discussed the device we might make together. And I said to Kostya, "Look, I can supply the gallium nitride. Can you supply the graphene? And I'll supply the postdoc. And we just do this without any fund, without a grant proposal, because I've got funding to actually do this." And he said, "Colin, I'll supply the graphene, you supply the gallium nitride, and your postdoc can assemble this transistor." And so Kostya did indeed supply the graphene, and Priti came over, and she arrived in 2015 in Cambridge. And I had a 5 centimeter, 2-inch diameter gallium nitride wafer. And I sent her up to Manchester, and Kostya supplied the graphene. And Kostya supplied a tiny flake of exfoliated graphene, which was transparent and you couldn't see it. And she tried to assemble this by hand, and she just couldn't make use, because she couldn't assemble it and put contacts on. And so after a few months, I phoned up Kostya, and I said to him, "You know, we just can't do this." I said, "Because the graphene is so small, it's transparent." I said, it will give us a much better chance if you could supply a 2 centimeter diameter piece of graphene, which matches my 2 centimeter, let's say it again. It would be much better if you could supply graphene 5 centimeter across, which would match the size of my 5 centimeter across 2-inch diameter piece of gallium nitride, so she gets a better chance. And Kostya on the phone, he just roared with laughter. And I said, "Kostya, why are you laughing?" And he said, "Colin, device quality graphene, 5 centimeters across, does not exist." And I just didn't know that, because I hadn't been involved with graphene research. And I just assumed that, you know, large area graphene must exist. So I went back, and from my phone, and challenged my research group. I said, there needs to be a new way to make large area graphene, because otherwise we haven't a hope of making graphene devices, electronic devices. And in my laboratory in Cambridge, we had 3 what are called MOCVD, research growth kits. MOCVD means metal organic chemical vapor deposition. One of these kits was funded by industry, 2 by EPSRC. And in May 2015, I had a senior postdoc called Simon Thomas in my group, and he came to my office. He said, "Colin, I have an idea to make graphene using MOCVD." And Simon Thomas, a really clever scientist, and he really understood the details of MOCVD growth. And so I said, "Okay, go ahead." And he said, "I want some growth gases." I had this flexible EPSRC grant called a platform grant. And so he was able to try this and use these gases, and he grew graphene using MOCVD. Now, why MOCVD, not CVD? And the main reason is that MOCVD is much more controllable than CVD for growth. You can see this in the price for equipment. So CVD equipment may be £200,000, or let's say $200,000 or euros. MOCVD equipment's over $1 million or euros. And it's much more expensive because you have much finer control over gas flows and so on. So he was able to get a growth window, which you can't get with CVD. He got this with MOCVD, and was able to grow directly on a substrate. with no metal catalyst. So we had graphene, which was not contaminated by the growth gases, and we didn't have to transfer it onto a substrate. We didn't have to put it onto copper in the first place. And so this was very lucky that I had the right person at the right time. I had this Indian student who had stimulated me to sort of do this. And in my group, I had the right growth equipment to have a new way of growing graphene. So we were the first in the world to successfully grow graphene using MOCVD. And I think at the moment, I believe, I may be wrong, that we're the only group in the world who successfully grows graphene using MOCVD. So I know some others have tried and failed. So, so he solved some key problems. And we took out a patent in 2015. So we had no metallic contamination, no transfer process. And so it looks promising for next generation transistors and biosensors and energy generation and so on. It looks promising because we have this large area graphene, but of course we don't know that it will work. And it's a bit like the structural graphene, as Harry has showed. You know, it's not useful when graphene is large. It's only when you have a small flake that graphene has high strength. So we set up a company to exploit this research, and we raised what's called seed funding in October 2017, moved into premises in 2018, and already we've got over 60 employees. So we're working very hard on this to try and get it to work. So for any of you interested in setting up a spin-out company, this is an interesting story. So it's cheap to set up a company in the UK anyway. You just register it at Companies House. I think it costs about £100 or euros or dollars. So it's very cheap. And the problem is, its premises in Cambridge are very expensive. So the Cambridge Science Park, and there's many Cambridge Science Parks, are almost full and they're very expensive. And we looked all over the country, and then we found a village north of Cambridge called Somersham, and a farmer has set up these sheds on his land, and he called it an industrial park. And it was a tenth to rent space in here. It was a tenth the price of renting space on the Cambridge Science Park. So we rented one of these empty sheds. And when we rented it, it really was an empty shed. It had 2 doors. It had no windows. So these windows you see in the photograph are windows we put in. It had no electricity. It had no water. I mean, it was really literally an empty shed. And when we moved in, we found it had a hole in the roof because it snowed that day. We moved in February 2018 and it snowed and the snow came through the roof. So, but we got the farmer to patch up the roof, and then we got electricity brought in from a power station nearby, a substation nearby, and we brought in water. And then inside this shed, we've got a really nice set of buildings. So you can put up these nice buildings inside. We've got a clean room inside this shed, for example. And so we're working to develop graphene into devices. And let me just say again, the benefits that we have, we've got no contamination, no transfer problems. We get monolayer graphene over a large area, can cover the substrate completely. We can dope when we grow, so we can dope the graphene. And in principle, it's suitable for high volume device production. In principle, suitable for electronic devices. And our first product, which our investors challenged us to do, was to solve the problem that Bosch couldn't solve. So they said Bosch couldn't scale up to make a graphene Hall sensor. They can only do it by hand. Can you scale up and make a graphene Hall effect sensor? So basically, most Hall effect sensors are made with silicon. And the question is, could we replace the silicon with graphene in a Hall effect sensor? So I think you all know about the Hall effect, and I'm looking at my watch, so I need to speed up. So, but the Hall effect very quickly is in this diagram, the cross that you see is the material. Many people use silicon, is the most common material. We're using graphene in the shape of this cross. And you have magnetic field perpendicular to the plane of the material, plane of the graphene. And then you apply a voltage at right angles to the magnetic field. And what happens is there's a Lorentz force on the electrons that run through this material because you've applied a voltage. The magnetic field puts a Lorentz force on, which moves the electrons sideways, and you generate a Hall voltage in the other perpendicular direction. So magnetic fields in one direction, perpendicular to that, you apply a voltage, And in the third perpendicular direction, you get what's called a Hall voltage. And there's a very simple equation relating these quantities. So if the magnetic field is unknown, you apply a known voltage and you measure the Hall voltage generated, and so you can calculate magnetic field. And so that's very simple to do. This shows you how Hall sensors are used. And many of them used. The typical car has up to 50 Hall sensors in for all sorts of applications. This shows you how you can measure on the left the speed of some rotating piece of metal, because the blue object on the left is a magnet, and then you have a Hall sensor at the front of that magnet, and the magnets generate a magnetic field. And when these pieces of metal cut through the field, they modify it, and that's detected by the Hall sensor, detects this change. Or on the right-hand side, you can see there's a Hall sensor in front of a magnet, and that detects when a gear wheel comes past. So you can measure the rotation speed of this gear wheel. So there's many applications. It's a non-contactless way of measuring a current in a wire, a wire flowing through, how a big wire like that, and carrying a current, and that current generates a magnetic field around the wire, and you can measure that magnetic field, and therefore you know what the current is. And so these now give you the sensitivity of the Hall sensors you can go and buy. So the silicon Hall sensor is 70 volts per amp Tesla. Compound semiconductors like gallium arsenide are better. They're also very expensive, 850 volts per amp Tesla. The Bosch graphene flake, if you look at their picture, if you look at their paper rather, which assembled by hand, not manufacturable, over 1,250 amps per amp volts per amp Tesla. A Paragraf graphene Hall sensor, 2,000 volts per amp Tesla. So it's 30 times better than silicon. So we have replaced silicon in this device. And also it can do things silicon Hall sensor cannot do. Our Hall sensor operates at 100 or less than 100 millikelvin degrees. So it's a cryogenic operation you can do as well as room temperature. The minimum you can get with a silicon Hall sensor is 230 K. Our maximum operation temperature is 450 K at the moment. It's highly radiation resistant. We can operate in magnetic fields up to 30 Tesla, and the maximum for silicon Hall sensor or gallium arsenide one is 1 or 2 Tesla. Very low power consumption. I put it 100 times lower than silicon. We now know our radiation result is 1,000 times lower than silicon. Really important if we can reproduce that in a transistor because of the energy savings. And we operate in a harsh environment. So this is high sensitivity. It's the best in the world it's the best in the world for a Hall sensor for measuring magnetic fields. Very wide operating field range, the best in the world operating temperature range, operates high frequency, high voltage, low power consumption. No planar Hall effect, which is really important, but I haven't got time to go into that. And resolution is parts per million in measuring magnetic fields. So this is a comparison of our Hall sensor with other magnetic field measuring devices. So the first row here is sensitivity, and it's very qualitative. So 1 tick means, sensitivity of silicon. 2 ticks then is specialist Hall sensor, that's gallium arsenide quantum well Hall sensor. Magnetoresistive, 3 ticks. Flux gates are very large and they are very sensitive. Nuclear magnetic resonance sensors very large, very sensitive. So our sensitivity is not as great as those, but not that far off. But on everything else in this table, the field range, no planar effect, low temperature operation, high frequency, low power use, we're much better than any of these in these other quantities. So I'm speeding up a bit in my talk. So this is very qualitative, but if you add up the number of ticks, which gives you sort of overall performance, then we have 29 ticks with a graphene Hall sensor compared with 11 and 12 and 13 and 11 for others. So it's overall performance much better than any other Hall sensor in the world. And we're talking with CERN about using that to measure the magnetic field in their next upgrade of the Large Hadron Collider, where they're having a 27-kilometer ring of superconducting magnets operating at liquid helium temperature. They're looking for 10,000 Hall sensors to map the magnetic field all around this ring as accurately as possible. Rolls-Royce are looking at our device for using in their all-electric engine for internal flights. we've got battery companies looking at our Hall sensor for detecting first signs of failure in batteries. And now I'm coming on to the conclusions. I think this is probably the last slide. So we have pioneered, we've got a new way to make low cost, high quality, large area graphene. It is the best performing Hall sensor in the world, and it's also manufacturable. So we're just starting to sell these devices. MOCVD grown graphene devices, it raises expectation that graphene biosensors and transistors, etc., may be manufacturable. So the question is, can graphene replace silicon as a better functional material in an electronic device? We've shown that as a Hall sensor, graphene has indeed replaced silicon, and we've got a better Hall sensor. And then this really is the key question: can now a graphene transistor replace a silicon one? And I do not know the answer to that. This is a research question, but there are indications, well, the indications are it's well worth trying to do this. And so this is something which in my retirement and with the company and with Queen Mary, I'm very keen to try to do. And I'm sure when Harry retires, he's not going to stop working. Harry's best years may still be to come, Harry. So it's a great pleasure to give this talk at your retirement celebrations. And thank you very much for inviting me.
Okay, thank you very much for inspiring talk, Professor Humphrey. So now it is time for questions. We have like 6 minutes or 5 minutes for the questions. Does anyone have anything?
June, could I ask a question?
Yeah, sure, why not?
Yeah. So Colin, you started with gallium nitride graphene transistor, okay?
Yes.
And you couldn't make it, but now you have the large area graphene.
Yes.
So what is the hurdle now in making transistors?
Right. So that's a really good question, Harry. So graphene is in principle a very simple material, right? So it's a single layer of carbon atoms. So it's one of the most simplest materials in the world in theory, in a way. In practice, it's extremely difficult to use. And one reason is that although lots of papers say it's inert, graphene, it's not inert at all. And the atmosphere affects it very strongly. So what happens is you have a piece of graphene prepared by any method, and it usually turns out to be N-type graphene. In the atmosphere, it becomes P-type graphene. So it absorbs on the surface oxygen atoms, it absorbs it absorbs water molecules, and they change the properties of the graphene a lot. So you have to, when you're making devices, the first thing is you have to avoid contact with the atmosphere, and you have to encapsulate the device. But anything you put the graphene on will change its properties. So you put the graphene on a substrate, and particularly if you grow it on a substrate, you get charge transfer from that substrate to the graphene, which changes its doping a lot. It means it changes its sensitivity. And also, quite remarkably, phonons in the substrate affect the mobility of carriers in the graphene. So, you know, we found out lots of these things, and some of them were known beforehand and sort of not published, but so it's really not easy to use. And so, so we're working, we've got a graphene transistor, which does work, but not nearly as well as a silicon transistor. And it's a question of improving this and finding out what the limitations are. And so far, I'm sorry, it's a long answer, it's a very important question. So far, what we've done is been mainly trial and error. And we now know we've just got to do basic science to understand what's going on. Because well, I'll just give you one example, which is an amazing example. You can dope graphene by waving it in the fumes of nitric acid. You can just open a bottle of nitric acid and wave the graphene over the top, and it's doped, right? And we just, in detail, we don't know what's happening. We know that something being absorbed on the surface of graphene which dopes it, and so so we need to do things like high resolution electron microscopy. We need to do scanning tunneling microscopy, and we haven't done these things yet. So these things you have to do, Harry. It's a really good question. It is difficult to make a graphene transistor, is my quick answer.
Thank you for that amazing talk.
Right, thank you, Harry.
Okay, Professor Humphreys, before we go on, there is a question in the chat. So Johnny Gu asked, is it right to say that the number of defects rather than the density of the defects in the material controls the strength?
Well, I think, I'm going to put this to Harry in a moment, but I think it's a really good question, because we know that in metals and alloys and so on, that the strength of those materials is largely controlled by the dislocations, right? And when you look at the graphene, then what the thermodynamics tells you is you're going to have point defects there, and may or may not have dislocations there. And again, we need to do the electron microscopy. So, the type of defect will certainly be important in controlling the strength of the graphene. But Harry, do you have some thoughts on this?
Yeah, so I think the big difference is the metallic bond. So when we actually deform a metal, we don't actually destroy the bonding. Yeah. But if you break any of the bonds in graphene, that's a permanent fracture. Basically, it doesn't reform when you deform it.
Right. No, that's a very good answer. That's right. And so graphene is very susceptible to cracking, right? So if you get a small crack in graphene, then it breaks very easily. So we've got a lot to learn about the mechanical properties of graphene as well.